Hello Math 1093, this is Dr. P with Logging Out. You will probably feel a little bit logged out after you've solved this equation here. So I wanted to make a video that was about solving logarithmic equations, because when we have an equation that involves logarithms to the same base, there is one strategy that works particularly well, probably better than all the others, and that is called consolidation. In other words, try to take some of the logarithms, or maybe even all of the logarithms, and combine them into a single logarithm. So that's what we're going to do with these two logarithms in this equation. We're going to try and combine these into just one logarithm. Combine into one logarithm. That's going to be the general approach. And to do this, we're going to use logarithm laws. So just as a reminder, here are some logarithm laws that we know about. If we have a log base b of u and a log to the same base of v, and add those together, that should be a v there, that's the same as the log base b of u times v. And also, if I have log base b of u minus log base b of v, that is equal to log base b of u over v. And then a couple more that are useful. One of them is if I have log base b of u and I multiply that by k, that is equal to log base b of u to the k. The uk. I love the uk. And finally, if I have a log base b of u, I can always convert that into an expression involving logs to a different base, as long as that base is common between the numerator and the denominator. And so those are the same base. And here I have the argument of the log function, and here I have the base of the log function that I had over here. So I'm just going to keep those in a box over here for future use. I'm not going to use all of them in this video, but I will use a couple of them very strategically. Okay, so let's take this equation and see if we can make some hay with it here. So I have log base 3, I'm just going to copy this, log base 3 of x plus 2 log base 3 x plus 1 equals log base 3 of 16x. First thing I'm going to do, I have this multiplier of 2 out here, and I know that I have a law that tells me that when I have a multiplier on a log, that's the same as taking a logarithm of a power. So I'm going to rewrite this as log base 3 of x plus 1 quantity squared. I've still got log base 3 of x over here, and I've still got log base 3 of 16x over here. Those haven't changed yet. Okay, so now I'm going to consider the fact that I have an addition of two logarithms, and I have a law for that too. If I add two logarithms, that's the same as taking the logarithm of their product. So I have log base 3 of x times x plus 1 squared. And that's the same as log base 3 of 16x. Okay, so now that I have everything consolidated, I could actually take this logarithm here and subtract it, but I'm going to do something a little bit different here. What I'm going to do is I'm going to raise each side, or let me rephrase that, I'm going to raise 3 to each side's power. So 3 to the log base 3 of x times x plus 1 squared. And I'm doing this in order to get rid of these logarithms. Equals 3 to the log base 3 of 16x. Okay, so the general philosophy behind what I'm doing here is I have some equation involving logarithms. I would pretty much prefer if I didn't have logarithms. So at this point, since each side is log base 3 of something, I'm going to invert that process by exponentiating to base 3. And once I do that, this exponentiation and the logarithm cancel out, and I get x plus 1 squared equals 16x. And now that's a nice little polynomial equation. Actually kind of a beastly one. I have to square x plus 1. That gives me x squared plus 2x plus 1. That's equal to 16x. And then multiplying that out, distributing gives me x cubed plus 2x squared plus x equals 16x. And then I can subtract 16x from both sides and get x cubed plus 2x squared minus 15x equals 0. At this point I have a cubic, which usually would be some cause for concern, but in this case I can factor an x out of the whole thing, get x squared plus 2x minus 15 equals 0, and then I can factor. I got x times, I believe that's x plus 5, x minus 3, and I know that that product is equal to 0. Okay, so now let's just step back and take a look here. I know that the product of these three numbers is equal to 0. If the product of three numbers is 0, then that means that one of these factors must be 0. because if I multiply three numbers and get 0, one of them had to have been 0. So I must have x equals 0 or x plus 5 equals 0, in which case x would be -5, or x minus 3 equals 0, in which case x would be equal to 3. So I have three possible candidates for solutions here: 0, -5, and 3. Okay, let me zoom out a little bit because there's one more thing we need to think about here. I would say that these are candidates for solutions. I don't think we've shown that they are solutions yet. These are candidates for solutions. Because there's one little thing that we didn't pay attention to as we conducted this whole process here. This equation that I started out with, the original one, this one, or I guess the one above it, they're the same equation. This has a limited domain. We can only take the logarithm of something if that something is positive. If any of these numbers, either x or x plus 1 or 16x, if any of those is negative, this equation is automatically false because that logarithm would then be undefined. So I need to look at these three solutions and think really hard about whether that equation is even defined for each of those solutions. Okay, so now I want to check each solution. Okay, so I'm going to check each solution. If x is 0, that's my first candidate. If x is 0, then the first thing I end up doing is I'm taking log base 3 of 0. Cannot do that. That is undefined. So x equals 0 is not a solution. Because the rule of thumb here is a solution is some value of x that makes this equation true, and this equation can't even be true if it's not defined, and log base 3 of 0 is not defined. Alright, so now I'm going to move on to my next candidate. My next candidate is x equals -5. Now I can already tell that that's going to create a major problem, because when I start substituting x equals -5 into that equation, the first thing I do is try to calculate log base 3 of -5. That is like even worse. That's even worse than trying to calculate log base 3 of 0. That is very undefined. So x equals -5 is not a solution. Okay, so now I'm kind of hoping, I mean, I guess this is just a scientific question whether this equation has any solutions or not, and I shouldn't get too invested in it. But I feel like I did all of this work, and if I don't get any solutions out, then I'm going to be kind of peeved. All right, let's try plugging in x equals 3 and see if that gives us any better luck. Okay, so if I plug in x equals 3, I get log base 3 of 3 plus 2 log base 3 of, what's 3 plus 1? That's 4, equals log base 3 of 16. 16 times 3. So is that true? Well, I can actually check, because this left side here is equal to log base 3 of 3 plus log base 3 of 4 squared. And then if I move that up a little bit, that is equal to log base 3 of 3 times 4 squared, which is log base 3 of, what is 3 times 4 squared? That's 16 times 3, that's 48, which, hey, that's the same thing as this. Those are the same. So this solution checks out. So the solution set of my original equation is just the number 3, nothing else. All right, so moral of the story, I guess there's really two major morals here. One of them is that when you see an equation with a bunch of logarithms to the same base, don't panic. Start consolidating using known laws of logarithms. That actually helps us make a lot of progress. And then once we get to the point where we have just one logarithm on each side, we can unpack that using an exponential function. We can get rid of that logarithm and get it down to something a little bit nicer, in this case a polynomial equation. And then the other major moral of the story is, whatever this process shows you as possible solutions, all of that is subject to whether this equation is actually defined at each of those solutions. In other words, is each solution in the domain of each side of the equation? And if not, then we have to cast that solution out. It's not really a solution. So this is one place where checking your solutions for actual validity against the original equation is super duper mega important.